Hello everyone, this is C. Sridevi, working as Assistant Professor in Electronic and Communication Departments at Martins Engineering College. Today I welcome you all for online video lecture. Today my topic is analog communication. Okay, analog communication. Let me start with the analog modulation. Okay, analog modulation is transmission of analog signals, from transmitter to receiver. Okay, before going to that, I just want to tell you the need for modulation. Okay, why do we need modulation? Modulation changes high frequency signal to low frequency signal. Low frequency to high frequency signal. Okay, actually, the first very we need is now modulation changes low frequencies to high frequencies. When we modulate a signal, it changes low frequency to high frequency. Then automatically the height of the antenna get increased, size of the antenna get reduced. And the second thing is when we modulate a signal, the signal which we transfer into the space where we feel very less noise. And the third is when we modulate a signal, the signal is get less interference. Okay, then the fourth point of the modulation is frequency division multiplexing. When we modulate a signal, we occur frequency division multiplexing. So that's why we need modulation. Now I introduce various types of analog modulation techniques. The first one is amplitude modulation. The first one is amplitude modulation, where in which amplitude of a modulating signal is changed to in accordance with the modulating information. The second type of modulation is frequency modulation, in which frequency of a modulation signal is changed in accordance with the amplitude of a carrier signals. And the third type of modulation is phase modulation, in which phase of a carrier is varied in accordance with the phase of a signal. Okay, here this is the amplitude modulation spectrum. Okay, the modulator is having two inputs. First one is modulating signal and the second one is carrier signal. And the output signal is called modulated signal. This is the diagram. This is called modulating signal. This is carrier signal. This is modulated signal. Okay, in amplitude modulation, amplitude of a carrier is varied in proportional with the amplitude of a modulating signal by keeping frequency and phase of a carrier signal completely constant. Okay, this is modulating signal, this is carrier signal, this is amplitude modulated signal. This is time domain representation of AM modulation. And here we see the frequency domain representation. In frequency representation, we have three things. First one is carrier signal, and the second one is upper sideband, and the third one is lower sideband. So when we transmit a amplitude modulation into the space, we see three signals. We send three signals, that is carrier signal, upper sideband and lower sideband. So the bandwidth of the AM modulation is upper sideband minus lower sideband, which is 2FM. Okay, the main problem with the AM modulation is it suffers with lot of noise, as here information is completely in the peaks. Okay, so when we transmit this peak information signal, it is easily affected with the noise. And the second modulation is the AM extension. Amplitude modulation are having three extensions. First one is DSB, second one is SSB, and the third one is VSB. In DSB, we transmit three signals. We transmit only two signals, that is upper sideband and lower sideband. So the bandwidth of the DSB remains same as AM signals. But when coming to SSB, the bandwidth in SSB we suppress one carrier signal and one of the sideband signals, and we transmit only single sideband. That is called single sideband modulation. And the advantage of SSB is, first one is bandwidth is reduced. That is exactly becomes half when compared to amplitude modulation and DSB modulation. And the second one is in single sideband modulation, as one of the sideband and carrier is suppressed, we save a lot of power. Power saving calculations are very easy and efficient. And coming to the third advantage, in the SSB, when compared to AM and DSB, noise effects are very less. This is SSB spectrum. Okay, this is USB and this is LSB spectrum. And coming to DSB, in DSB, we transmit only two sidebands and we suppress the carrier. Okay, and that's why we save the bandwidth of the DSB is twice the modulating signal frequency. And coming to the next extension of AM modulation is VSB. VSB is vestigial sideband modulation. As the name itself indicates, in VSB we transmit vestige, that is part of one full sideband, and vestige of the other sideband. This forms VSB signals. Coming to applications of AM, SSB and DSB, AM is suitable for radio broadcasting. SSB is suitable for voice signal communication, and DSB is suitable for radio broadcasting. Coming to FM, frequency modulation. FM is frequency modulation. The standard range of FM is 88 MHz to 108 MHz. And the definition of frequency modulation. In frequency modulation, we vary frequency of a carrier in proportional with the amplitude of the message signal by keeping phase and amplitude of a carrier signal completely constant. FM standard range of FM is 88 MHz to 108 MHz, and the FM main application is it is used in radio broadcasting. Okay, coming to the spectrum of FM, here this is time domain. Here this is called modulating signal, this is called carrier signal. See here, FM is varied in, that is frequency variations we see according with the amplitude of the message signal. Okay, when we see the FM signal, the FM spectrum consists of infinite sidebands. FM is again divided into two types, narrow band FM and wide band FM. Now, next overview of amplitude modulation. Here, amplitude modulation is again three things. First one is amplitude. In amplitude modulation, the advantage is its simplicity, design and operation. Coming to benefits, AM is very simple to design and it is very less prone to noise interference. Next, frequency modulation. In frequency modulation, we see frequency of a modulating of a carrier is varied in proportional with the amplitude of message signal by keeping phase and amplitude of a carrier signal completely constant. Now we see the comparison of different modulation techniques AM, FM and TM. In TM, we vary phase of a carrier in proportional with the amplitude of the modulating signal by keeping amplitude and frequency completely constant. Here we see the differences between AM, FM and TM. First one is bandwidth. AM is having 2 FM bandwidth practically, which is very high. This is one of the disadvantages of FM. Now coming to FM, FM is having infinite bandwidths, infinite sidebands in the positive side and infinite sidebands in the negative side. So coming to bandwidth wise, narrow band FM bandwidth is 2 FM and the wide band FM bandwidth is infinite. Now coming to PM, it is medium, intermediate between AM and PM. Okay. Speaking in terms of FM, narrow band FM where beta is less than 1 and in wide band FM where beta is greater than 1. So to make it bandwidth practicable, we use Cardson's rule. Cardson's rule we applied to make infinite bandwidth signal to finite bandwidth signal. When we make the bandwidth of a signal finite, we can able to send the signal into the space. This is bandwidth. So overall bandwidth performance, AM is medium, FM is burst and TM is intermediate. And standard frequency range of AM is 555 kHz to 1655 kHz, FM is 88 MHz to 108 MHz, and AM voice signal range 300 kHz to 3.5 MHz. Coming to real-time applications, AM is completely suitable for video broadcasting, FM is for radios, and VSB is for TV video broadcasting. And coming to signal quality, when we speak about signal quality, AM is having all the information in the peaks. When we send the information signal which is having peaks into the space, it is easily affected with the noise. Coming to FM, that's why AM suffers with lot of noise. Coming to FM. Coming to FM, in FM when we transmit the signal from transmitter to receiver, when even though the noise effects are in the peaks, we have the option to eliminate that noise by using amplitude limiters. But our information inside the FM signal is safe and secure. That's why FM suffers with very less noise compared to AM and PM. And in PM the noise effects are intermediate, because in PM the information resides in terms of phase. That's why in PM noise effects are moderate. Now coming to complexity. The only main advantage of AM is it is simple to design. We just need resistor and capacitor combinate to generate AM signal. That's why, except one advantage, AM is having all disadvantage. Coming to FM, FM signal generation is very difficult when compared to AM signal, and PM is also very high because there we use phase discriminators. That is 90 degrees phase shifters we use. And coming to AM applications, AM we use in radio and telemetry, FM, radio, TV, audio, and PM we use it is in advanced communications. See here, I said vestigial sideband is particularly suitable for TV broadcasting. Already we know the video range of our real signal is 0 Hz to 4.5 kHz. So when we send this signal, that is one full sideband and part of the other sideband into the space, when they mix, overall design effects will look like that. That is, the part which we lose here will compensate which we generated here. So the overall spectrum in frequency domain of VSB shaping filter would look like this. That is, it also accepts the signals which are low frequencies. That's why VSB is exclusively suitable for video kind of transmission in televisions. When now speaking to SSB, in SSB, we send only one sideband suppressing one carrier and one of the other sideband. See here, in SSB we send only one sideband. We suppress the carrier and one of the other sideband. So when we transmit this signal, and the shape of the real SSB signal would consist of some gaps. So say suppose 300 Hz to 3.5. Means overall the gap would look like 600 Hz. Because of this gap which we find here, we can conclude that this type of modulation is suitable for exclusively voice kind of communication. And coming to FM, when we observe the FM signal and its spectrum, here it is suitable for transmit high frequency signals. The carrier used in the FM is high frequency range, that is under between 88 MHz to 108 MHz. Because of this high frequency carrier, this is particularly suitable for FM radios, and the FM radio range is 88 MHz to 108 MHz. Finally here, three different type of modulation of analog olden form of communication are SSB exclusively for voice, VSB for video transmission, and FM modulation is for radio broadcasting. Now, coming to applications, evaluation bandwidth. The bandwidth of AM is 2 FM. Okay, when we speak bandwidth, we can speak bandwidth in two ways. First one is single tone and second one is multi-tone. In single tone, we take the modulating signal as with single frequency, that is AM cos 2 pi FM. Whereas in multi-tone, we consider M of t as group of frequencies. So bandwidth for AM in single tone is 2 FM and in multi-tone is 2 omega, where omega is the highest frequency of the modulating signal. So bandwidth of AM is twice the highest frequency of the modulating signal. Whereas in FM, the bandwidth is again we speak in two ways. First one is narrow band FM and the second one is wide band FM. In narrow band FM, modulation index, that is beta, is less than 1, And in wideband FM, the modulation index beta is greater than 1. In narrowband FM, the bandwidth of narrowband FM is 2 FM and the bandwidth of wideband FM is infinite. So we cannot able to transmit the bandwidth which is infinite. So by using Carson's rule, which says that Carson's rule says that the particular amount of bands only we transmit into the space, suppressing the other side bands. Say in Carson's rule, the one which are having low efficiency will suppress and we transmit only the finite amplitude signals into the space. So by using Carson's rule, we make the bandwidth of AM signal, that is FM signal, to infinite to finite. Coming to signal quality. In AM, all the information resides in only peaks and that too positive peaks. So that's why in AM, the positive peak signal is called envelope signal, which is called envelope. In AM, all the amplitude resides only in the envelope part. So when this signal is transmitting from the transmitter to receiver, this signal is easily affected with the noise, and we do not know by ourselves whether it is because of variation or because of noise. So that's why we conclude that the information which is affected in the AM signal is very severe. That's why we don't use this AM for general broadcasting communication. This AM is completely ruled out. Coming to FM, our information is inside, which is very safe and secure. So even though when it is affected with the noise, we have the option to remove this noise by using amplitude limiters. That's why FM noise effects are very less. Now coming to PM. Here, phase of a carrier is varied in proportional with the amplitude of the message signal by keeping amplitude and frequency of a carrier signal completely constant. Now, I will discuss what a basic introduction to modulation and give what are the different differences between all the modulation techniques. Okay. Now here, the three modulations. First one is amplitude modulation, second one is frequency modulation, and the third one is phase modulation. Okay, coming to amplitude modulation.
Full screen here.
The basic modulator is having two inputs. First one is modulating signal and the second one is carrier signal and the third one is modulated signal, which we represented with S of t. Modulating signal is represented with M of t. And other names of modulated signal is low frequency signal, audio signal, information signal and baseband signal. Coming to the second input to the modulator is called carrier signal, which we use a very high frequency carrier. And the output is called modulated signal, which we represented with S of t. In time domain, we represent modulated signal as S of t, and in frequency domain, we represent modulated signal as S of f. Modulating signal in time domain, we use the shape like this, and in frequency domain, we represent the modulating signal frequency like this. 0 to some few heads this positive side and 0 to some few heads in negative side. This is representation of modulating signal, that is first input to the modulator, and second input is carrier signal, which we fix high frequency carrier. And the signal, in frequency domain, we use the same shape based on the carrier parameters. Based on the carrier parameters, the modulation techniques are divided into three types. That is, first one is called amplitude modulation, second one is called frequency modulation, and third one is called phase modulation. In amplitude modulation, we vary amplitude of a carrier with respect to the amplitude of a modulating signal by keeping frequency and phase of a signal completely constant. So the shape of the amplitude modulation signal would look like this way, complete shape. And we represent this signal with S of t. And when you observe this signal, positive shape exactly resembles our information shape. That's why this positive signal in the AM signal is called envelope. And for AM signal, for three cases I will show you. No, case one when mu is equal to 0, which is called no modulation. When mu is greater than 1 is called under modulation, and the signal of the amplitude modulation shape for under modulation case is this one. And the third case is mu is equal to 1, which is critical modulation, and the shape of the AM signal in critical modulation is this one, where positive peak and the negative peak touch exactly. This is mu, and when modulation index is greater than 1, the AM signal will overlap like this. So these are the three different cases of amplitude modulation. This is under modulation case, this is critical modulation, and this is over modulation. When we analyze these three signals, in second case, that is under modulation case, we use practically for demodulating the signal, because in AM the positive peaks and negative peaks in under modulation have some sufficient gap. So it is easy for us to demodulate or distract the signal from demodulation. When coming to critical modulation, the positive information and negative information exactly touch each other. So it is difficult for us to design a demodulator to remove this information and get without any distortion. Coming to over modulation case, here positive wave and negative wave overlap each other and this makes noise. So we don't use practically to receive this signal, that is over modulation case. These are the three cases of AM modulation. Now coming to FM modulation. AM is having all disadvantages. First one, noise problem. In AM, information is in the peaks, so it suffers with lot of noise. And the second disadvantage is AM bandwidth is twice the message signal bandwidth. So when we transmit AM signal into the space, it occupies double the message signal bandwidth, which is unnecessary. And coming to third disadvantage, in AM along with the carrier, we send two similar sidebands, that is USB and LSB, and these two sidebands carries same information, that is USB and LSB carries same information. So why to send two same signals again and again into the space? But we are using AM, the same technique. That's why AM we don't completely rule out. And coming to fourth, AM consumes lot of power, as it is having three signals. Carrier, which does not carry any information, it consumes 66% of the total power, and remaining two sidebands which have the same information also consume more power. So finally, because of these all advantages, AM is completely ruled out except one advantage, that is the simple to design. AM is simple to generate and simple to demodulate. Now coming to FM. FM. First for FM modulator, first input is modulating signal and the second input is same carrier signal, and the output is FM signal, that is modulated signal. Okay, same here also modulated signal is always real signal which is low frequency range, and carrier signal in FM is very high, which is in the range of megahertz. The carrier frequency of AM is kilohertz, that is from 555 kilohertz to 1655 kilohertz, whereas carrier frequency of FM is 88 megahertz to 108 megahertz range. So when compared to AM, as we are using here megahertz range carrier, obviously it is affected with the less noise. And in FM, carrier of a frequency of a carrier is varied in proportional with the amplitude of the message signal by keeping amplitude and phase of a carrier completely constant. Okay, so the FM signal in time domain would would look like. Only we see frequency variation. We don't see amplitude variations and we don't see phase variation. So when we transmit this signal from transmitter to receiver, even though when it is suffers with the noise, we have option to remove this noise signals by using amplitude limiters. We don't have, that's why even though when it is traveling into the channel, it is affected with the noise, but we have option to eliminate this noise completely zero. That's why FM is suitable for radio broadcasting. And the standard FM range is 88 megahertz to 108 megahertz. Based on the modulation index, the modulation index of FM is represented with beta, which is kf AM by FM. The modulation index represents how much modulation we are doing. Beta is equal to 0 means no modulation, modulation is not yet started. Beta is equal to 1 means critical modulation. Say beta is less than 1 means under modulation, beta is greater than 1 means over modulation. The modulation index of FM is directly proportional to amplitude of the modulating signal and inversely proportional to frequency of the modulating signal. Based on this modulation index, FM is divided into two types. If beta is greater than 1, it is called narrowband FM. If beta is greater than 1, it is called wideband FM. The practical modulation is wideband FM. Now I will show you one video of AM, FM and PM. So here in AM, amplitude of a carrier is varied in proportional with the amplitude of the modulating signal by keeping frequency and phase of a signal completely constant, whereas in FM only we vary frequency, and in PM we vary only phase. That is, in AM only amplitude will carry the information, in FM frequency will carry the information, and in FM phase variations will carry the information. So here this is called M of T signal, low frequency signal, which is also called information source. All the real informations come under the low frequency category. The real information signals are three types: audio, video and voice. The audio range is 20 Hz to 20 kHz. The video range is 0 to 4.5 kHz and the voice signal range is 300 Hz to 3.5 kHz. And this transducer changes non-electrical signals to electrical signals. And transmitter. The main heart of the communication log diagram is transmitter. Transmitter, it changes low frequency signals to high frequency signals. Here this is AM modulated signal, where only amplitude changes will carry our information signal. If the channel is space, then it is called wireless communication. If the channel is wide, then it is called wired communication. And this is receiver. Receiver, the main function of the receiver is to demodulate the signal. That is, it changes high frequency signal to low frequency signal. And this is output transducer, which changes electrical quantity to non-electrical quantity. This is overall block diagram of communication system. Now, the next is amplitude and phase and frequency modulated signal. Here in amplitude, the information goes in amplitude part, whereas in phase modulation, our real information travels in terms of phases. Amplitude is constant and frequency is constant. We will not touch other two parameters. In FM, our real information, that is M of T signal, will go in terms of frequencies. We don't touch amplitude and we don't touch phase. Only frequency changes will carry our information. This is digital form. Next, amplitude, frequency, phase modulation is Again divided, this is the overall block diagram. Here I am modulating signal. Real modulating signals are three types: audio, video, voice. Audio signal means what we hear. Video signal means what we see. Voice signal means what we speak. The voice signal range is 300 Hz to 3.5 kilohertz. The transducer changes one form of signal to another form of signals. When the signal is transmitted into the space, the transmitter will transmit. If it is wireless communication, the transmitted signal first goes to the antenna. Antenna changes electrical signal to electromagnetic signal. This is today these are the topics which we discussed: AM, FM and PM. Thank you.